What's happening, dogs? Mr. Allen here with some application of exponential functions. We got a bacteria culture that is growing exponentially. That's exciting stuff. In 3 hours, the amount of bacteria grew from 4.2 grams to 10.6 grams. Write a function to model the growth per hour. That's important right there, per hour. And then predict the amount in 10 hours. Okay, so let's see here. We got to figure out what percent it is growing by. And the way we could do that is by taking the new amount, dividing it by the original amount, okay? So 10.6, divide that by 4.2. Let's see what we get there in the calculator. 10.6 divided by 4.2. All right, so I get 2.52, but that's over the course of 3 hours. So if I take this right here, which is a nasty decimal in my calculator, if I take that and I raise it to the 1/3 power, I will get it per hour that way, okay? So now I'm going to raise this. I'm going to hit the caret button. It's going to take that answer from my calculator, right? The 2.523, all those decimals. And then I'm going to raise it to the 1/3. So 1 divided by 3. I can just type it in like that. You don't have to do like the alpha x or alpha y equals to get the fraction. We can just do straight up division there. So I get 1.3615, okay? So this is going to be 1.36, we'll go 2. Okay, so that would be what I'd have for my base of this exponential function, all right? So we'll say our population, we just do like the amount A of t equals the initial amount of 4.2 grams before it started growing. Then we'd have the 1.362 raised to the t. A lot of times they're going to ask for just t up here, or sometimes they'll say a b value, a capital B value of 1. That way there's no like t divided by 3 or t divided by 2 or whatever, okay? So you just want t. That way here I can just plug in a number, that number of hours. In this case we're going to do 10 hours here into this function. We'll get an estimate, okay? Now I'm going to go ahead and use the value that I have in my calculator here, okay? There's a couple ways to do this. Number one, I think the easiest way, if we're only going to do one estimate, is just to type 4.2. Then I'm going to go parentheses, arrow up, hit enter, close them, and then we'll raise this to the 10th power, all right? Because t is currently in hours because I did the cube root of it, or sorry, the 1/3 power of it, the cube root. So we get 91.92, okay. So when we did 10 hours, 4.2, and then we really used the 1.36. It was originally 1.5, so I'll put like a dot to say it's like, hey, it's the number that was in my calculator, and raise that to the 10th power. I end up with 91.925, so we'll say 0.9, since these were all in just a tenths place. So 91.9 grams. Awesome. All right. Lovely stuff. There we go. So get used to using your calculators on these, right? Know where your exponent button is, your caret there right below the clear button. That's going to be super helpful for any kind of exponential stuff because you want to type in any exponent that you want. Now, one other thing you could do is you could take this value right here that we had, if we're going to say use it elsewhere, like if we were going to graph with it, what you could do is you could hit store down there on the bottom left, right above the on button, and I'll just store it as B for my base or whatever, right? And now it's there. So I could even do 4.2, and then I could just do alpha B, raise it to the 10th, and I'm going to get the same exact answer that I had for this one here, okay? So that's a cool thing to know on your calculator, is how to store a value. That becomes really helpful with different applications, especially as the math gets a little more complicated. All right, that's it for this one here. Let's do the second problem over here on the right. We got the population of a town is decreasing exponentially. In 2 years, the population went from 4,500 to 1,125, or 1,125. Write a function to model the population decrease each year. So per year, once again, just like this one was per hour, predict the population in 7 years. Okay, so similar process, right? I'm going to take the new amount, the 1,125 people, divided by the 4,500. And then because this is in 2 years, I'll raise it to the 1/2 power, which will get me the base for a 1 year model situation. All right, so let's type all that in. I can just do it all at once. 1125 divided by 4,500. You could do a fraction. You don't have to. Division works just fine. We'll raise it to the 1/2 or 0.5. Hit enter, and we get 0.5. Okay, so it's a 50% decrease. Dang. People are leaving this town fast. Maybe the taxes are too high. You know, I feel that in Illinois. Anywho, 0.5. Nice, easy number. Okay, so now let's write our function here. I've got AFT for a population model, amount of people per time, right? Our initial was 4,500. We just have 0.5 or 0.5 if you'd like, raised to the t. Now it's asking in 7 years. So A of 7, right? This is just function notation, we call it, okay? The amount of people after 7 years. Right? There's no like multiplication going on. There's no math happening on the left-hand side here. Function notation just tells us what we're like working with in the problem. So you got 0.5 raised to the 7th power. Let's type it all in. I don't think I need to store the 0.5 this time. So you got 4,500. Let's see here. Parentheses 0.5 raised to the 7th power. There's going to be nobody left. So we got 35 people. Everybody's out, right? There's like the one angry person's like, I'm not leaving my house. You know, that person. That person is still there, right? I grew up in this town. Anywho, I feel like it's like every movie right there. So 35 people. That's better. 35 people after 7 years. Nice. Well, there we go. Not so scary if you know what you're doing on these. There are other ways to come up with your base here. That's just one of the ways of doing it that I've seen some people do. I've seen them done other ways, but this way works. All right. So there we go. I hope you guys enjoyed this wonderful video here. Make sure you like it, subscribe it, tell people, keep watching, and stay dope.